Have you ever wondered what makes up everything in our universe, from the air we breathe to the stars in the sky? It's an atom, an incredibly tiny particle that serves as the building block of all matter. But don't let its size fool you. Inside this microscopic entity lies a world of complexity that has been keeping scientists intrigued for centuries. It's like peeling an onion, each layer revealing a new and more intricate detail. So, are you ready? Join me as we dive into the fascinating world of atoms. Imagine a miniature solar system. Now replace the sun with a dense nucleus, and the planets with tiny particles called electrons. Welcome to the fascinating world of atoms, where it's like gazing into a miniature solar system. At the heart of this system, instead of a glowing sun, we find a dense nucleus. This nucleus, though tiny, is the heavyweight champion of the atom, accounting for almost all of its mass. It's packed with protons and neutrons, particles that carry a positive charge and no charge respectively. Now picture the planets in our solar system following their paths in orbit around the sun. In the atomic world, these planets are electrons, particles with a negative charge. They're much lighter than protons and neutrons, and they orbit the nucleus at varying distances. These orbits, or energy levels, determine how electrons interact with each other and how atoms bond to form molecules. It's hard to grasp how incredibly small an atom is. Try to visualize a grain of sand. Now imagine that grain of sand magnified 1,000,000 times. Even at this scale, an atom would still be smaller than the period at the end of this sentence. Yet, despite its minuscule size, the atom is a bustling hub of activity. Think about the vast emptiness of space in our solar system, the great distances between the sun and the planets. This is mirrored in the atom, where most of its volume is empty space. The nucleus is like a tiny speck in the center of a huge stadium, with the electrons as specks whizzing around the outer edges. What's more, these electrons are constantly in motion, orbiting the nucleus at mind-boggling speeds. It's a ceaseless dance that forms the basis for everything in the universe, from the air we breathe to the stars in the sky. Isn't it remarkable that such a tiny particle can hold so much complexity? Now let's look closer at the three key players that make up an atom: protons, neutrons, and electrons. Our first key player, the proton, is a subatomic particle with a positive electric charge. Protons reside in the heart of the atom, a region we call the nucleus. They are like the sun of our miniature solar system, the atom. Their positive charge is crucial to the structure of the atom, as it attracts the negatively charged electrons in a sort of cosmic dance. Next up, playing a neutral role in this atomic drama, we have the neutron. Like the proton, the neutron also resides in the atom's nucleus. Despite having no electric charge, don't underestimate its importance. Neutrons act as a sort of atomic glue, holding the protons together in the nucleus. Without neutrons, the positively charged protons would simply repel each other and the atom would fall apart. Our final key player is the electron. Electrons are much smaller than protons and neutrons and carry a negative electric charge. They orbit the nucleus much like planets orbiting the sun. The negative charge of the electrons is attracted to the positive charge of the protons in the nucleus, keeping them in their orbits. The interaction between these three particles is what gives an atom its properties. The number of protons determines the type of element the atom represents. The combination of protons and neutrons gives the atom its atomic mass. And the arrangement of electrons in their orbits determines how an atom will interact with other atoms. These three particles, protons, neutrons, and electrons, are the building blocks of every atom. And every atom is a building block of matter. They are the stars of a microscopic universe that is as complex and fascinating as the cosmos itself. So there we have it, the three main characters of our atomic story. You may ask, if all atoms are made up of the same particles, how do we differentiate between them? Great question. We use two key identifiers for atoms: atomic number and atomic mass. Let's start with the atomic number. This is simply the number of protons in an atom's nucleus. It's like the atom's ID number, unique to each element. For example, hydrogen has 1 proton, so its atomic number is 1. Oxygen, on the other hand, has 8 protons, so its atomic number is 8. The atomic number is fundamental in defining the element. Now let's move to atomic mass. This refers to the combined number of protons and neutrons in an atom. Unlike atomic number, atomic mass isn't always a whole number. That's because it's an average, factoring in the different isotopes of an element. An isotope is a variant of an element that has the same number of protons, but a different number of neutrons. For instance, carbon, generally, has 6 protons and 6 neutrons, making its atomic mass 12. But there's also an isotope called carbon-14, which has 6 protons and 8 neutrons. The atomic mass of carbon, then, is a slightly higher number due to these heavier isotopes. So, to identify an atom, we look at both its atomic number and atomic mass. Just like a person's name and ID number, the atomic number and atomic mass give each atom its unique identity. Despite centuries of research, the atom continues to be a source of mystery and wonder. This tiny powerhouse of energy is still not fully understood, despite being the building block of everything we see, touch and feel. What we do know is that atoms are incredibly complex and dynamic, constantly in motion, and capable of interacting in ways that are both predictable and utterly surprising. Today's researchers are pushing the boundaries of our understanding with the help of quantum physics. They're exploring the behavior of subatomic particles, the strange and fascinating world of quantum entanglement, and the concept of superposition, where an atom can exist in multiple states simultaneously. The implications of this research are profound. It could lead to new technologies, new ways of generating and storing energy, and perhaps even new insight into the very nature of reality itself. Who knows what secrets the atom still holds? One thing is certain: the journey to unravel them will be a fascinating one.